Hey guys, in this video we're going to run through a few examples using U-Substitution to do integration. So U-Substitution in general as a concept is just taking a complicated looking function such as this one that we don't have any good rules to use to integrate and rewriting the function in terms of another variable u times the derivative of u du. So if we can make this function look like u du, we can perhaps make it look simpler and thus easier to integrate. So this will become clear as we do examples. I think perhaps the hardest part of U-Substitution is really knowing when to use it. So I have a few criteria that you can sort of check in your head as you're assessing a problem. So the first one is there are no other easy ways to take the integration of the function. So perhaps you look at this function and you think, man, there really are no rules that I have memorized in Calculus 1 that would allow me to easily take the integral of that function. And then the second and most important part is that one part of the function looks like the derivative of another part of the function. This is key, and this is really what U-Substitution says. We've got u, which represents one part of our function, and then du, which is the derivative of that part of the function. So in this case, we've got integral of 2x over the square root of x squared plus 1. So does one part of this function look like the derivative of another part of the function? Well, yeah, the numerator 2x looks like the derivative of x squared plus 1, right? So if I see that something looks like the derivative of something else, I make this u, and obviously I want to make this du because that looks like the derivative of u. So I'll make x squared plus 1 equal to u. Right? And I don't want to worry about the square root. That's part of the beauty of U-Substitution. I don't really have to worry about anything outside of my u. In general, you want your u to be a very simple expression like x squared plus 1. And then du is the derivative of u. So this will be x squared, the derivative of that is 2x, and then the 1, we take the derivative of that, it goes to 0, so it disappears, and then we'll tack on always a dx at the end of that. So here's our u and our du. So now we want to rewrite this function in terms of u and du, like this, right? So if I want to rewrite the function in terms of our new variables u and du, well, I know that u is x squared plus 1, so really to get that down here, I want to put that in the denominator and say the square root of u, right? And that's what our original function looked like. And then what about, I need a du to go along with my u. So does that take care of the rest of the function? So du was 2x dx, and yeah, that's 2x dx. That takes care of the rest of it, right? So I can just put a 1 here as a placeholder. So now, look what I've done here. This is very important because this is key. I've really done a U-Substitution problem at this point. This is the hardest part. I've taken a function, I defined my u, and then I wrote my du, and then I rewrote the function in terms of my new u and du. Now this function is equivalent to this one based on these definitions, but it's a lot simpler and it's a lot easier to take the integral of. So let me show you how you would take the integral of this, and I think you would know how to do this one. So 1 over the square root of u is the same thing as 1 over u to the 1/2 power, right? So the square root is the same thing as the 1/2 power. We'll write my du, and then 1 over u to the 1/2 is the same thing as u to the negative 1/2 du. And now we simply use the power rule to take the integral here. So what you do is you add 1 to the exponent. So I'll say negative 1/2 plus 1. The way we'll do that is negative 1/2 plus 2 over 2. So that'll be positive 1/2. So that's our new exponent. And then I divide by that same number, right? That same exponent. So I'll divide this by 1/2. And then plus c, right? So I can simplify this a little bit. I've got a fraction in the denominator. That's a little messy. So I can actually say when you divide something by 1/2, that's the same thing as multiplying it by 2. So this is really 2u to the 1/2, which is really 2 square root of u. And we have to add our plus c in here. So this is how we took the integral of 1 over the square root of u du. So now this is our integral here. So the final step is to substitute back in our u. So our final answer will be 2 times the square root of x squared plus 1, and then simply plus c. That's our final answer. So see how we used U-substitution to rewrite this integral in a simpler form. We take the derivative of that simpler form and then simply plug back in our u. So that is U-substitution. Alright, so I'd like to work through a slightly more difficult example problem up here. So I've got a function 10 times the term 3 minus 2x to the 5th power. So again, I check my criterion quickly mentally in my head. There are no other easy ways to take the integral of this function. You know, you look at this function, this is fairly complicated, right? 10 times a term raised to the 5th power. You know, we really don't have any easy rules like, you know, for example, the product rule or the chain rule like we had for differentiation. Integration, we don't have any easy way to do this. So does one part of the function look like it could be the derivative of another part of the function? Well, this is the more subtle part to see, but once you get good at these and you do enough practice problems, you can see that if I define this term inside the parentheses as u, so if I define this as u, and in general it seems like for these problems you can't go wrong by at least guessing that u is something inside the parentheses raised to some power. That seems to be a pattern that generally will hold true, but again, that's not a rule. So our du now, and you know, perhaps this isn't the right way to choose u. Let's just test this out, because this is oftentimes how you'll solve these problems. You'll pick something for u, it won't really help you, and you'll have to pick something else for u. So du here would be negative 2 dx, right? Because the 3 goes away, and negative 2x, the derivative of that is negative 2. And you can see here that if we wanted to write our function in terms of u here, like u du, so we've got u, and we know that's got to be raised to the 5th power, and then times 10 dx. So we're going to put in a du here, right? And our du is negative 2 dx. So how do we make this look like 10 dx? We have to modify it slightly. So if I just put in du here, as I always have to do, I always have to have a u du, and I have that. I already took care of this exponent of 5 for the u. But how do I make this negative 2 into a 10? Well, I can multiply it by negative 5, right? So I'll have to put a negative 5 out here in front of the integral sign to accommodate this negative 2. So see how this u to the 5th power takes care of this part, right? And then the du takes care of 10 dx as long as we multiply the negative 2 by negative 5 to get to 10. Okay, and we can always keep these numbers, these whole numbers out here, outside of the integral sign, and they'll sort of just stay along for the ride. They won't really need to be integrated, and they'll multiply through at the end. So now we have a much simpler looking function to integrate. So in order to integrate this, we'll say u to the 5th, so the power rule says we can take u to the 6th over 6, and then again, this is going to be times minus 5 plus c. So now we've done the hard work, right? We've found a function that we can use to represent this one in a simpler form using u and du. We took the integral, and now all we have to do is plug back in our u. So this will be equal to negative 5, and then 3 minus 2x, sorry, it shouldn't be a minus sign there, to the 6th power over 6 plus c, right? And you can even rewrite that more simply with the negative 5 in the numerator. Negative 5 times 3 minus 2x to the 6th all over 6 plus c. So we have successfully integrated an initially complicated looking function using U-substitution. All right, one last example problem here. So I've got a function up here for which U-substitution will be useful. So I can look at this function and just mentally say, you know, there are really no other easy ways to integrate this. You know, unless you happen to know any, this is a pretty complicated looking function. And the second mental criterion we know to check for U-substitution is, does one part of this function look like it could be the derivative of another part of the function? Well, I see there's kind of two terms here. I kind of see this function in two groups. There's this and this, right? And if you notice here, in this term, we've got an x to the fourth, and then an 8x and a 3. And if we were to take the derivative of what's inside here, we would get 4x cubed plus 8, and then the 3 would disappear. Well, in this term, we've got x cubed plus a number, right? Well, it seems like this looks suspiciously close to the derivative of this. So if I call this u, then perhaps the rest of the function could be du, or the derivative of u, and this could work out well. And there's another little clue here. So remember I mentioned the general pattern that if you've got a term raised to an exponent, you generally can't go wrong by at least guessing that this might be u, because it's a big term all raised to an exponent. And if it doesn't turn out to be u, you can simply go back and reassess and see if something else could be u. But let's at least try this out here. So let's say u equals x to the fourth plus 8x plus 3. Thus our du will be 4x cubed plus 8x, and then this is dx tacked on the end. I'll change this 3 to a little more legible. So now I want to rewrite my function in terms of my new definitions here with u. So again, I want to use this general form here, integral of u du. So I know u, if it's this, needs to be raised to the 1/3 power, right? And then du, if I tack this on at the end, does that take care of the x cubed plus 2? Well, if you notice here, 4x cubed plus 8x is really similar to this, but it's raised to a factor of 4. So if I want to represent x cubed plus 2 by 4x cubed plus 8x, and remember this dx here is going to take care of that dx, I could multiply this whole term through by 1/4. And if I multiply it by 1/4, I can put that out front here. So notice how I've modified and accommodated for this factor of 4 here. So if I divide this by 4, it'll be x cubed. If I divide this by 4, it'll be 2. So that's the same thing as multiplying by 1/4. So very similar to the last problem where we have to adjust for a factor in our du. So now we've got a simple looking function, right, that we're ready to integrate. So if I want to integrate this, this is going to be 1/4 stays on the outside, and then u to the 1/3 power, we know we can apply the power rule here, where we add 1 to our exponent. So 1/3, whenever you add 1 to a fraction, you want to take the denominator and say 1 whole is 3/3, and then that'll be 1/3 plus 3/3, 4/3 for the new exponent, and then we divide by that same number. That's how you do the power rule for integration. Okay, so now we've got an ugly looking fraction in the denominator here. So to get rid of that, we'll use the rhyme, you know, dividing fractions, don't you cry, flip the second one and multiply it with the other fraction. So this will now be 1/4 times, remember we have to flip it, 3/4 times u to the 4/3. And remember, always add your integration constant plus c. So now all I have to do is multiply out these fractions, and this is going to be top times top, 1 times 3, 3 over 16, u to the 4/3 plus c. So now all that's left, I plug in my u in terms of x, and I'll have my final answer here. So this is going to be 3 over 16 times u to the 4/3, so I'll plug in my whole u, x to the 4th plus 8x plus 3 all to the 4/3 power plus c. So this is my final answer. So I really hope this video helped you guys out. If you have any questions, please direct them towards me at facebook.com/denovotutoring, and I'll see you guys in the next video.